Welcome back for some more business math. I know you're excited, right? All right, we're going to start Introduction to Limits, which actually starts calculus. So hold on tight, it's calculus time. As I mentioned before in kind of the introduction, that when you deal with algebra, you're dealing more with static things, where calculus is more dynamic, which is kind of nice because we could examine something at a particular moment in time that's changing, and that's what we're trying to look at. So let's see what the big hoopla is about limits. A limit helps describe the behavior of a function, f of x, when x is close to a particular value. Now this is very, very important. It does not say the value of the function. It says what is happening with this function as x is getting close to a particular value. So if we had this graph and 2x minus 1, you can tell it's a line either by graphing it or just by looking at it. It's that form y equals mx plus b. Okay, and so if I wanted to look at this and said what is happening as x is getting really close to 2. Well, how close is close? Well, what if I'm at 1.999? Well, it looks like f of x is 2.998. Well, what if I'm 2.001? Well, it looks like x is 3.002. So it appears as x is approaching 2, meaning as it's getting really close, that the value of the function is approaching 3. And that's what a limit is. A limit says, I don't care what the value is, because you're going to find out there's going to be some times you just can't plug that 2 in. And so what happens as we get close to 2 with our function? It's approaching 3. And of course this is easy to see graphically. We're saying as we get really close to 2, what is the value of my function getting close to? And it's getting close to 3. So we can look at a graph that's continuous, and it's easy to find the limits by just simply, as you're getting close to x, look up at the graph and read the y value. So we love continuous functions, which we'll talk more about in 10.3. So what's the big deal? Why should you even care about limits? Have you ever wondered why these stripes on a 1 liter measuring cup are about a millimeter apart? I know you have, right? And we're going metric on us here. If I have a 1 liter measuring cup, a right circular cylinder with a radius of 6 centimeters, the volume of the liquid that we put into the cup is a function to the level h, where the volume equals pi times r squared times h. Well, I just said that my radius was 6 centimeters, so I have a function here. What I want to do is ask how close must we measure that height to measure out 1 liter of water, because you know you cannot get exactly 1 liter. I used to laugh at my husband. He would try, when he was measuring, say to get 2 cups, he would get down real low and try to get level and try to look and see, am I exactly at 2 cups? Well, you're never going to be exactly right. You might be a little over, you might be a little less. Well, it depends on what you're doing, if that's that big of a deal. If you're making, instant mashed potatoes, it might be kind of bad if they're a little runny or if they're a little thick. But again, it's dependent on what you're doing. So in this case, we're going to measure out 1 liter of water, which is 1,000 cubic centimeters, with an error of no more than 1%. Because we feel like 1%, no big deal. If you're over 1% or under 1%, my potatoes are going to be fine, right? And so that would be my 10 cubic centimeters. So in other words, I want to know at what interval to hold the value of h. Remember, that's the height, that's the level of my water that I'm putting in this measuring cup, to satisfy this inequality. So this inequality says that the volume, well, we already have that. We said that's 36 pi h, so I can plug that in, minus this 1,000 cubic centimeters to stay within 1% needs to be less than or equal to this 10 cubic centimeters. Well, if it's been a while since you've done some algebra, when you do absolute values with inequalities, you take this 10 and you do the plus and minus of it, and you get rid of the absolute value. So that's a little something to dust off the cobwebs, right? If you don't remember that, when you have an inequality with absolute value, you take this value 10 and you do the negative and the positive, and this stays in the middle. Now what I'm trying to do is isolate h, because that's what I'm trying to figure out. H needs to stay between what values? So I could add 1,000 to all three pieces, because that cancels out the 1,000 in the middle. And next I can divide all three pieces by 36 pi, because again I want to isolate h, which is what I did. And I stick that in my old trusty calculator, and I get the lower end I round up, the upper end I round down to even get my interval nicer, and I get this 8.8 and 8.9. So what does that mean? Well, that says we should hold the interval 8.9 minus 8.8, which is 0.1 centimeters wide, 1 millimeter, which gives about 1% accuracy, which is certainly more than enough in cooking, and why the measuring cups are the lines are a millimeter apart. Alright, so let's go back to our first example where we said we wanted to know what the behavior of our function f of x equals 2x minus 1, what was happening as x approaches 2. And we looked at it and it said, you know, if you were very, very close to 2, it looked like the function was approaching 3. How you write that all math and nerdy as a limit is the limit of 2x minus 1 as x approaches 2 is 3. So the definition is you have a limit of some function as x is approaching some value, okay, let's just call it c, whatever value, equals the limit. And so notice with this example is pretty easy, because we could just simply plug in the value of x into our function and we could find the limit, because if I plugged in x is 2, I get 2 times 2 is 4, and 4 minus 1 is 3. So if I want to find the limit of this function, if you can, just simply plug in the value. So I plugged in 2, and I can see that this limit is 4. Now this is very, very important, and why students usually struggle with limits is the existence of a limit at a particular value of c has nothing to do with the value of the function at c. It's what is happening as we are getting close. Because as you're going to see, some examples come up where you can't plug in a particular value. For example, find this limit, absolute value of x over x as x approaches 0. Well, what happens if you plug in 0 for x? Look at that denominator. Oh my goodness, your math destroyed a city. You cannot divide by 0. So this is the part that's important with limits. Well, what if I get close to 0? Really, 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 really close. Well, let's check out and let's see what the graph looks like. So if I look at the graph, I can see that it's split, and it actually has a jump here. So what's happening as x approaches 0 from the left, and what's happening as x approaches 0 from the right? So looking at this graph, we certainly can see different things are happening depending on which side we're approaching 0 from. So if I'm approaching 0 from the left, I'm getting a different value than if I'm approaching it from the right. So this is what we call one-sided limits. So we write the limit of f of x as x approaches c with a little bitty minus sign up there equals some limit. And that little bitty minus sign means we're approaching from the left of x. So if I'm interested in x equals 0, then I'm looking at how I'm approaching it from the left of 0. Well, if we have a limit approaching from the left, then it probably would make sense. We could also analyze what if the limit's approaching from the right, and that's where you see this little plus sign. So this just simply says if I'm approaching some value, x is approaching a particular value from the right of that value, I can get a particular limit. Ordinary limits, what we started this conversation with, are two-sided limits. We just don't typically call them that. We just call them limits. And they must be defined on both sides of C. So in other words, the function must approach the same limit from either side. And how we define ordinary limits, two-sided limits, is the limit from the left must equal the limit from the right, and then you have our limit. So if the left-hand side equals the right-hand side, and something about the hokey pokey, right? Then the limit exists. So this is sometimes how you figure out if the limit exists. Find the left-hand limit, find the right-hand limit. Are they equal? If so, guess what? The limit exists. All right, well, let's go back to this example. What is the limit as x approaches 0 from the left? Well, here I go. I'm approaching from the left of 0. It looks like the value of my function is approaching -1. Well, what about from the right? Looks like to me it's approaching a +1. So what is the limit? Since the left-hand side, -1, does not equal the right-hand side, 1, the limit does not exist. All right, let's look at a graph to see how we can find limits. So this first one says, as x is approaching 2 from the left. So as I'm approaching 2 from the left, what is the value of my function approaching? Well, I kind of follow my function along here, and as I get really close to 2 from the left, it looks like the value of my function is approaching 2. Let me get a little laser pointer action going here. So I'm approaching from the left, I'm approaching 2. Here I go, away I go. I get really close to 2 from the left, and I can see the value of my function is 2. All right, well, what if I'm approaching it from the right? Well, if I'm approaching it from the right, then here I go from the right, and I can see up here, it appears that the value of my function is getting very close as x is approaching 2 from the right, is getting very close to 5. Well, what's the limit as x approaches 2? Does not exist, because the left-hand side does not equal the right-hand side. And you're going to see there's, graphically it's kind of easy to see, because if it's not continuous and you have a jump there, which we do, then the limit's not going to exist. There's different limit properties. The limit of the identity function. So the identity function is just y equals x, or f of x equals x. So in other words, everywhere you pick an x, guess what? Your y is going to be the same thing. So if I'm at x equals 3, y equals 3. So for example, for the function f of x equals x, I want to know what the limit is as x approaches 2 of my function, which is x. Well, we just said on the last slide that for every x value I pick, the y value's the same. So if I'm approaching 2, then my y value is going to be 2. If I have a constant function, notice no matter where I'm at, it doesn't matter which x I'm approaching, my function's going to always be approaching this constant value itself. So if I had the limit of 5 as x approaches 2, so in other words that's y equals 5 by the graph, I can see as I'm approaching 2 or as I'm approaching any number, the value of the function is 5. Here's some properties of limits. These are kind of nice because it gives you ways to break down if you have like multiple functions. We just said the limit of a constant is simply that constant. Okay, so just talked about that. And then we have my limit of my y equals x. So it's whatever x is approaching because x and y are the same. 3 here and 4 says if you're adding two functions, you could simply add the limits. 5 is really nice because it says you can pull that constant out front. So if you had something like 5x, something like that, that can be pulled out front. Part 6 says the product of functions, if you want to find their limits, you can find their limits separately and then multiply the limits. The quotient says you can bring the limit and find the limit of the numerator, the limit of the denominator. And then the last one here is with radicals, that I can actually bring this limit inside and then take whatever square root and so on. All right, so let's put some of these limit properties to the test. I said that you could split up when you're subtracting and take the limit of each function individually. Also said that the product, because x squared means x times x, right? So I could split those up. This 4 is a constant, so I can bring it out front. Well, now we have all the definitions I've given you. This is my y equals x. Okay, each one of these. So as x approaches 3, the limit of x is 3 times the limit of x, 3, minus 4 times 3. So each one of these are my y equals x, so I'm approaching that value. And I can see I get -3. Now again, if you can just simply plug in the value, then plug it in. There are times you cannot plug in the value, dividing by 0, taking negative square roots, things like that. But what this tells you is for any polynomial function, the limit of f of x as x approaches c is just simply plugging in that value of c. So what you do is you look, you have a limit question here. This says I have a function. As x approaches 2, what is my function approaching? Well, if there's no reason you can't plug in a 2, plug in a 2. So I plugged in a 2, 2 cubed, 8, minus 10, minus 1, and I get -3. How about this one? Can I plug in -1? I don't see why not. I'm not going to get a negative under my square root. So as you can see, the first one, x cubed, that was a polynomial. Under this root here, x squared, that's a polynomial. And then this last one here, rational function, I simply plug in these numbers and it gives me that limit. So that tells me for any rational function r with a non-zero denominator, okay, so as long as when I plug in that x approaches 4, as long as I'm not dividing by 0, it's okay. I can just simply evaluate my rational function as my x is approaching the particular value.